Hello everyone, here we are for the next session. Next session we're going to be working with the inputs and outputs. We're going to go down quickly and we're going to revisit the defining inputs and outputs. The addressing of inputs is the I and a Q for outputs, and the analog inputs are on the peripheral I/O range. Then we'll talk about forcing I/O and what the problems are, and then we'll discuss how we map the I/O into dBs, and then finally we will go and program the I/O mapping, and we'll just discuss again what happens when things go wrong, how we will not use forcing, but we'll do it a different way. Okay, right, so if you remember, we spoke originally about the addressing spaces of the Siemens PLC. Basically, remember that the digital inputs are in the I, the address is I, and they start at 0.0 and they go to 0.7, that is a byte. And then the next byte starts at 1, 1.7, and all the way up to, depending on the size of the PLC, say up to 255. That would be 0 to 255. It's 256 bytes, 128 words of I/O, which is not a lot of I/O. And the peripheral input words, peripheral output words typically start above 255, so at 256, and they are words, so they are 2 bytes, they jump in twos. Let me just go to the next. Remember when we spoke about the individual bits, there's the individual bits of input byte 0, and it goes from 0 to 7. Then input byte 1 is the same, 0 to 7, and so on and so on. If you now want to just use the individual I/O, you use input 0.0. If you want to use the byte, it's input byte 0 or input byte 1. Then when you're going to be trying to use the whole word, it would be 2 bytes, input byte 0 and 1. See, we always try and keep on the even boundary because it's binary, it's 2, so it's even. So it's just better to talk about input byte 0 and 1 as input word 0. Rather, don't start at input word 1, which is byte 1 and 2. That just, it's odd. And then you can also address the inputs as double words. Input double word 0 is input byte 0, 1, 2, and 3 all together. As 0.0 is the least significant bit, and 0.7 is the highest, the most significant bit, they call it. So the whole bit pattern here would be one input double word, and this is input 0.0 is the least significant bit, and input 3.7 is the most significant bit. That's if you want to do some quick I/O addressing, that's the way you do it. And it's the same for the outputs. The outputs work exactly the same, it's just not an I, it's a Q. Then for analogs. Analogs in the older range of the PLCs, the S5s, the actual analog signal coming in, let's say it was a 0 to 20 milliamp signal, or 4 to 20, or a 0 to 10 volts. One of the things that you need to go and research is, of all the different input signal ranges, which is the most the best use of, would it be a 0 to 20 or a 4 to 20 or a 0 to 10 volts, etc. But anyway, in the old S5 PLC, it would give you a signal, a number in the PLC, in that input word or peripheral input word of 0 to 4095, which would say on a level transmitter would be 0 to 100%, which gives you a resolution of 0.02%. That's pretty good. I mean, your level in a tank, you're not going to be looking for 0.02%. And you want to see it, say, greater than 95% or less than 1%. You're not looking for that resolution. If that input sensor was in at RPM, say 0 to 4,000 RPM, it give you a plus or minus 1 RPM resolution. On the newer PLCs, the S7, they're giving you a 0 to 27647, which is 12 bits. So the 0 to 100% sensor would give you 0.0036%, which is meaningless. On your screen, if you're going to show so many decimal places, those last decimals that are flickering is meaningless. And RPM, again, you can see you're getting 0.1 RPM, which is okay. But we don't really work in those. I would suggest your RPMs are not that critical. If you've got special, in my view, if you've got a specific thing that you're looking for RPM, a turn or something, you would then use an encoder, which gives you a much better resolution. Right, so let us go and go back to the PLC, and let's just think about how you would configure I/O. So if you remember the little plant we used an example last time, it was a tank with a pipeline with a pump and a drain valve and a supply valve going to another tank. And so we had we had a pump, and then in the second tank we had motor one, which was the agitator. So we allowed for 5 motors and 5 valves for spares in future. All right, so let's go to our PLC. What we will do, I'm just going to go to OB1. What I've done is I've stripped out all the other example programs, because we're now going to start building our program for a real plant, or the new machine, the Tim's incredible machine, TIM. So we just got the 2 parts that we developed, the global timers for that 1 second pulse, remember, and the group safe starts, which we spoke about before. We will now add to that. So now what we want to do now is we want to go to this part of the configuration of Siemens, go to hardware. Now you can see it's showing us the hardware which we configured, which was just the CPU, and there's no I/O in this rack. So I'm going to now go to, in this Explorer, I'm going to go to 300, because this is a 300 PLC. We're going to go to the I/O. You can see now you have different I/O types, analog input, analog outputs, in and out, analog. So I'm going to go and put in a digital input card. You can see there's a whole range of input cards. And you see the moment I click on it, Siemens is telling you can put in any one of those slots. So if you can see, there's actually 8 slots. But when you're going to go and fault find in a PLC, you're going to see the CPU in the rack, and then you're going to see I/O cards. So although in the PLC it's showing slot 4, that would say typically be rack 1, slot 1, and this will be 2, 3, 4. So we can put in 8 cards, so it'd be rack 1, slot 1 to rack 1, slot 8. And the reason why I would suggest you think like that is because when you go and look at the rack, you're not thinking, is it input 0.2 or is it input 55 point something? You want to know which slot it's on, which channel it's on. So we will develop an actual geographical addressing for this I/O. So this will be rack 1, slot 1, and we're going to put in a 32 channel DC 24 volt card. I just put it in straight. If I just double click on it like I did there, you see it's automatically assigned it to address 0. So that, like I said, is going to start at 0. So that's going to be input byte 0, 1, 2, and 3. So it's automatically assigned it. If I go to the next slot and I double click, it's going to put the next addresses 4 to 7. So what are we going to do is we're going to put the motor run feedbacks and all the other I/O for the motors on the first card, the I/O for the valves on the second card, and then in the future, as we develop this further, we're going to put some nice little level switches or flow switches, and we will put them onto the third card. So we will have 3 input cards, and the addressing is 0, 4, and 8. Okay, so now we want an output card. So if I go to the outputs, I'm going to also put in a 32 channel DC card, and I'm going to probably just make it a 0.5 amp output. So we will want to use some sort of interposing relays. or directly to the junction box to the valves. So if I click on that slot, I'm going to put in a digital input card. You can see it's now changed it to 12. It's continued. I'm going to go and change that address. See, it says system default. I'm going to make that 0. So it's still, so this is output 0.0 to 3.7. You can see that's rack 1, slot 1, slot 1, rack 1, slot 2, rack 1, slot 3, rack 1, slot 4 will be the output card. Then I'm going to go and put in an analog input card and analog output card for as we develop this further. So let me go and put in a simple 8-channel 12-bit card. Let's go on and put it at 320. Let's go and make that 256 like we said in our example. That's an analog input card. And we'll go and put in an analog output card, and we will use an 8-channel. There it is. And we will just change that address back to 256. Okay, so like what you see now here is that this will be input 0.0 to input 11.7. This will be output 0.0 to 3.7. This will be peripheral input words 256, 258. Remember, it jumps in twos. This will be peripheral output word, etc. So now, once I've defined my I/O, I can go and save it. I do a compile here, save and compile. Everything's hunky-dory. I've got my I/O. I go and, okay, so now here we have our program. How do we address the I/O? If I go into my OB1 and I just go and add a rung in here, let me put it in there. I'm going to put a rung in there, and I'm going to say, let me change the ladder, and I'm going to put in there input 0.0, and I wanted to go to an output Q 0.0. Everything's great, but there's no symbols. So we haven't actually got any distinction. So yes, you can go here, go edit the symbol, and you can say it's the run signal 01, it's a Boolean, and it's the run feedback of motor 001. Okay, then I've got a comment, and I've got everything. So this one I can do the same, and I can say this is the motor output 001. It doesn't make sense to have the run feedback control the output, but just for programming sake, I now have some symbols. Okay, so everything's got a symbol. It's a bit silly, but there's our symbols. But let's go and find out where those symbols are stored. So if I go back to my manager, if I go to the program, you'll see there's an option there called symbols. I open it. You'll see now, literally, there is the input that I defined and the output that I defined. And so, yes, you can now go and manually put in, say, run 02 is going to be a Boolean, and it's, oh, no, that's not right. Input 0.1, which will be the next one, it's a Boolean, and you can copy this one here, and you change that to 2, and you can carry on typing there and save it. And if I literally go back to my program, I can maybe put another one and change that to 2, and it's fine. See, if I change it to raw, see how it's picked up the symbol, but that's fine. But going to our symbol list like this is very laborious. So what you can do, you can export your symbols, and I can make it, say, TIM2, and there are different options, ASCII, sequence. See, there's no CSV. Siemens, like I said, I think I've told you this joke before, there's 3 ways of doing things, the right way, the wrong way, and the German way, and Siemens has designed it like that. So if I go to TIM02, if I go into my Explorer, it's in Documents, TIM02, where is TIM02? If I open it, there is the format, and there's my I/O, and you'll see that this is a tab, and then it's got the address, then there's another tab, this symbol, and then another tab. So you can now pull this into Excel and go and put in all your symbols for all your I/O, save it back. Excel won't save it back as this type of files. You have to save it as a text file. Then you have to go and edit it in Notepad again to get it back to this tab format. A little bit laborious, but I've done that, and I'll show you what I did for this. So I gone and created all the I/O for our little incredible machine, and there you see I've literally labeled the I/O, and there's the rack 1, slot 1, channel 1 in the comment. And then these are the spares, so the symbol is the same. So if you ever use this, straight away you'll know that, this one wasn't configured before, so I'm just going to put a symbol on it, give it a comment. See now, there's the I/O for the motors, the run feedbacks. The second card has got the limit switches open and closed for the valves. And then I've left the next cards spare, 8 to 11. Then I have the outputs for the motors. We've only got one digital output card, so I've used byte 0 for the motors, and I've started at byte 2 for the valves. And so I have got that. So what I can do now is I go back to my symbols. I'm going to literally delete these symbols that I created, and I'm going to import my little symbol. So I've created it there. If I open it, import, yes, there's no errors, bang, and there are all the symbols. So literally I've now imported all my I/O, the inputs and outputs. I save it. I can close my symbols. If I literally now move across this, and that I/O will see, now it's got the rack 1, slot 1 in it. If I put the symbols on, you can see there's a whole comment of what that shows you: rack 1, slot 1, channel 1, rack 1, slot 1, channel 2. Now notice I made it ones, not zeros, because when you're counting, you say first channel, second channel, not zeroth channel. I know in binary, we all think binary, but some technicians, etc., when they're looking at the PLC, they just say it's the first channel. They don't think of addressing. So anyway, that's just a minor thing. All right, so now we have the I/O symbols configured. So now we know we've configured the I/O, we've configured the analogs. Okay, we haven't done symbols for the analog inputs, but we will do that. So then the next thing is now what we want to do is we want to take that raw inputs and outputs, and we want to put it into DBs. So we will create a DB11, which is the digital inputs. So this is inputs. I started at 10 for I/O, input, outputs. O is outputs, 1 is inputs. And we're going to create a DB structure which is going to mirror our actual I/O. Then we will do the same for the analog inputs and outputs. We start at 20 for the outputs and 21. So we can go back here and we can go and define a new object, data block 11, and we can call it I/O, okay, DB I/O map digital inputs. And then I can go in here and I can literally start. So it's a little bit laborious, but you can go to the symbols. You can copy this, go here, paste it, make it a bool, take that out. You can go back to the symbols, copy that, go there, Control V, and so on and so on and so on. So again, I'm quite lazy, so I will use the best program in the world. I will go and Siemens allows you to actually, let me just save that. If I save it, I can actually generate a source file of this, and then I can go and edit it again in Word or Excel. I can start doing some formulas. I'm just going to go and show you now. I've created these source files again. So if I go to my DB11, I've created the source file. This is the format, so you don't change this part. You then put the actual symbol like this. There's the actual tag. It has a colon, boolean, and the // is the comment, and there literally is copy one-to-one of all the inputs. So if I now go and I'm literally go and what they say, compile it, you see it's no errors. So now if I go back to my Explorer, go back here to DB11, there it is. I've actually created the DB literally one-to-one what the I/O looks like. I've done one for the digital inputs, which is source code DB10. I'll just do a compile here, and if I go and open DB10, see it's got no symbol, but I can just copy this one and I'll go there, digital outputs, and if I open it, there literally is a copy of one-to-one of the I/O. Okay, so there, that is the digital inputs and outputs. Let's just save it. I will literally just go and open the, I did a DB20 and 21, which we haven't got any analogs in our little example program, but I'm going to generate these two. Compile. I will go and open my new DB20 and 21, and there it is. I'm just going to copy this, go here to 20, make this analog output, go to this one, that's analog input, and if I open those two blocks, there is the analog output structure, is the analog input structure. Okay, so what we're going to do is we're going to now basically do a mapping program. We're going to map input 0 into DB11, DBX 0.0, and the same for 0.1, and the same for 0.2. And we're going to do the same for the outputs. We're now going to write the DB block out to the actual output, so on. So that is what we're going to do. So let us go back to our program. I'm going to go and close my symbols. I'm going to just go back to here. So now I want to create some mapping. So as you see, we've created DB10, DB11, 20, and 21. We're going to go and create a new function block, FC11 say, and that's going to be IO map digital inputs. And if I go in here now, I will literally do this one-to-one. I'm going to read in input 0.0, and I'm going to write it to db11.dbx 0.0. You can see now I put the symbols are on, so if I just switch them off now, you see it's input 0.0 to 1.1 to 0.0. So if I go and copy and paste this to a few, and now we just be clever, we're going to make that a 1, 2, 3, 4, 5, 6, 7, and we don't want these, so we just delete them. We go over here, we make this a 1, 2, 3, 4, going the wrong way, 5, 6, 7. And if I put the symbols on again, there we go. If I put the comments, now you can see I'm literally writing the input 0.0 into this DB block. It's got the same symbol. So now in my program, everywhere in the program, I don't need to use IO, and this is the key. I will be using the DB11, DBX 0.0 in every reference to that input for the run feedback, and so on and so on. Okay, so I've also done a little bit of work here. So I'm going to close that. I'm going to go back to my sources. I've created an FC11, and you can see literally I've gone and copied and pasted and changed the noughts to ones, to twos, to threes, and I've literally done, if I just go back to the top, there's the comment, rack 1, slot 1, rack 1, slot 2, and rack 1, slot 3. So if I compile this, everything's fine. I go and open my FC11 now. There it is. So I've literally now mapped every IO. All my inputs are now mapped into DB11. I don't put on all the symbols there. Literally, it's exactly 1-to-1, the input to the DB. And if you guess what's going to happen next, if I go and create, and if I just copy that one and I say rename FC10, I'm going to just do this. Digital output O, and I go to my sources. I've got an FC10. I do a compile. Bob Zeronti. Go to FC10. And now what I've done is, remember it was rack 1 slot 4 in our configuration. I closed it, but open it again. Remember this was slot 1, 2, 3, slot 4, rack 1 slot 4 is now my IO. And literally I'm now copying the DB 0.0 to the actual output. So everywhere in my program, I will not be using the outputs, I will be using the actual DBs. Now let me go and explain why we do that. All right, here we have it. So let's say we're happy, we've done a 1-to-1 mapping, everything's great, we've mapped the IO, and now we have a problem. Let's say the input 0.2 channel blows on the input card. So now we have a problem. What's going to happen is you can't bridge it because the actual input on the card is broken. Can't shut the plant down because there's maybe a batch in it, etc. So now we have to do some modification. Now, if the input card is typically blown, no bridging, no forcing, there's actually, well, forcing you can do. The problem with forcing is that if you ever have to reload the program, all your forces are gone. So now you don't know what you forced. So it's better to actually go and say, okay, I'm going to drop that one away and I'm going to use a spare channel, say input 1.7. I'm going to map it to my original 0.2. So let me go and do that as an example. So I'm going to close that one. I'm going to call up FC10, FC11, sorry. Oops, not that one. It's this one. All right, so I'm going to switch off the symbols quickly. Okay, so let's say this one is blown. So what I'm going to do in my program, I'm going to put double slash in there, which is a comment. And then I'm going to put in and input 0.7. But what did I say? 1.7. And then literally if I save and copy it and download it, so I'll put the symbols back on, you can see that one is spare. We could then go and technically go and change the symbol to say this is the old, this is now bridged or something. But the actual program which uses this run feedback, we don't have to change anything because we've changed the IO mapping here. So we don't have to go and search for this input anywhere else in the program. It literally is done once. Okay, so then let's say we have a shutdown. We take that bridge off and we change the input card. We can go and literally take the comment out, save it, and we're back to where we were. All right, so now we've got FC10 and we've got FC11. The problem is now we haven't got an OB1. So what we're going to do now is we're going to just delete this one, and I'm going to now we're going to do map inputs. And I'm just going to put it in statements, and I'm going to call FC11. So literally now, if I have now the safe starts and I have another part of the program for the drives and the vowels and the sequences, and then right at the end, I'm going to do another thing. I'm going to map the outputs, and I'm going to literally call FC10. So now so OB1 is going to now scan the global timers. It's going to work on that 1 second pulse. It's going to then map all the IO into the DBs, DB11 and DB21 for the analogs. Then we will go through all the programs referencing the DBs. Then right at the end, we will then write the output DBs to the IO. So between this network and this network, these calls to all the other functions will not reference any physical IO. then you don't have to change anything if there's a problem, except either in the digital input mapping or the digital output mapping or the analog input and output mapping. Makes it very simple. So again, the analog inputs, remember we addressed it as peripheral input word 256. We're not going to create a DB with all 0 to 255 as dummy variables to line it up. So you will see a slight difference there. But if I go back and I go to my sources, here's my FC21. It literally does a load peripheral input word 256 and puts it into DB21. If I compile that, I can literally go, I'm just going to do the same for the analog outs, close those two. I'm going to just go back to my program. There I have a FC20. I'm just going to copy that comment again. I'm going to make it analog outputs. Go there. Enter, and this is going to be analog inputs. All right, so now if I go into this one, you'll see literally it's done the same. There, that's what it is in raw code. There's the symbols and there's the comments. So we don't have anything configured, so it's just dummy variables. And the same for FC20. There they are. So literally it's copying DB20 back out to the peripheral output words and so on. So now I'm going to go and put that into my OB1. So here I will call FC21. So now I've literally mapped my digital inputs and analog inputs, done my program, and then at the end, I write the DBs back to the physical outputs. And there is the program. Okay. So we've done the same. We've done a one-to-one mapping. Remember, if an analog input channel blows, you then do a rewire and so on. Okay, so just as a reminder, what happens in the program, we're going to do our global programs like timers and flags and sirens. And then we're going to map the inputs. We're going to do all our programs referencing the the input DBs, and writing to the output DBs. And at the end, we're going to map the outputs back out to the output DB, sorry, to the physical outputs. Then it'll go round, around, around. So just a reminder, everywhere in this part of the OB1, all those functions, all those blocks do not reference physical I/O at all, which makes your life simple, because if you have any problems, you just do it either in the inputs or the outputs, and you can do your rewind. You can even force it in there. Now, I remember forcing, I have a very bad, had lots of bad experience of forcing. So we will actually talk about that a little bit later, that we will not do forcing. All right, so what I want you to do quickly is go and just look in your plants or the programs you're working on. What type of I/O cards have been used, what you've seen being used, whether they're using analog, AC as a signal. What's good about AC I/O cards is you don't have to have a 24-volt power supply. The problem with AC is that, especially in plants with dust and static, that can cause some nice explosions. So we would stick to the 24-volt DC as a rule. Some plants use 48-volt DC, but that's very old now. On the analog inputs and outputs, as you can see, there's different versions of signal. The key problem you have with the 0 to 10 volts and the 0 to 20 milliamps is when the signal is broken. Let's say the wire is broken and it shows a 0. You don't know if that's the real reading. So the most common, safest analog is to use a 4 to 20. So when it is at 0, it's actually giving you 4 milliamps. So when you have less than 4 milliamps, you know there's a problem. The sensors are either faulty or the wire is broken. And you can also get a 1 to 5 volt DC. The plus and minus is for things like for some adjustment rheostats or buttons that you use, but that's another day. Right, I showed you how we would map 1 to 1. the inputs into the DBs and the same for the outputs, and what we would do when we have problems instead of forcing. And remember, the rule of OB1 is you do not use any references in the program, in the programs following the mapping, because you want to just have one place to go and change it. So that is basically what we do, the rule of OB1, and so we will continue the next time. Happy hunting with your homework. Ciao for now.